Good morning. Thank you for coming for this, the second day of the LA-CCI conference. We have now an invited talk by Leslie Pérez Cáceres. Leslie is an associated professor at the Pontificia Universidad Católica de Valparaíso in Chile since 2018. She is also the director of the Artificial Intelligence Diploma of the same university at the School of Ingeniería Informática. She received the Master of Science degree in Engineering Sciences in 2011 from the Universidad Técnica Federico Santa María and the PhD in Engineering and Technology Sciences from the Université Libre de Bruxelles in 2017. Her main line of research is the automatic configuration of optimization algorithms, and she's one of the developers of the iRace configuration tool. Leslie, you have the floor.
Gracias. Sorry, I should go in English now. Hello, nice to meet you again. If you saw me the other day in the summer school, my name is Leslie, right? I was very well introduced, and I'm going to talk to you about automatic algorithm configuration, which is the main thing I try to do when I do research. Right? Okay, we just go straight to explain what is algorithm configuration, right? And just to mention the things that we need to pay attention to when we talk about this task that can be modeled as an optimization problem, right? So just to put us all in the same mind spot, right? Optimization algorithms, but also other techniques, right? Other computer programs. When we design them, we have to choose things, right? So we have decisions that we need to take in order to design them, right? And normally when we design optimization algorithms, we take into account these design choices, and we have to select different components normally because in general there is already a good body of research, right? So you can actually take some inspiration from literature and implement these components. And then you want to find the good behavior of these components and then understand how they interact, right? So you can get a good algorithm in the end. So this is what we normally do. And parameters are just design choices, basically, that we postpone for the moment of execution, right? When we want to just decide when we execute the algorithm, and not during the design process, right? So this is kind of like a lazy approach to design. One could decide basically everything, right? Design could be postponed completely to the moment of application. And actually, this is what we call automated design. Later I will show you, right? So why somebody would postpone these design decisions is actually because of flexibility. We want to have techniques that are flexible enough in order to handle different problems and solve them efficiently, right? So we expose different parameters in order to give these degrees of freedom, right, when we are executing the algorithm. And this causes, right, that algorithm performance is indeed very dependent on the settings you use to run the algorithm. This is a direct consequence of this. So this is the kind of like how we would see the configuration task. And the other day, not so long ago, actually, a couple of months ago, I was giving a similar talk in the diploma. And I thought, well, this is not very relatable now because not a lot of us have ever faced this kind of task. But in the end, I thought, okay, this is more easy to understand. An algorithm is like a washing machine, right? And a washing machine, I remember the one that my grandmother had before. It just had one button, right? So on and off, right? This was the design options that were left there in order to be adjusted at the moment that I was washing clothes, right? And now I have all these design choices that are put in this machine, right? So this is just the same thing, right? These are design choices. I can choose how quick goes, when I'm drying things, right? What is the temperature, etc. So this is the task we are faced every time that we try to solve algorithms, right? So what we want is to get algorithms that are effective, right? And for doing this, we have to decide where to push all these buttons, and we want to configure them, right? So this is the main motivation, right, for automatic algorithm configuration. So the configuration task is the task in which we try to find parameter settings that have the best empirical performance that we can find, right? So we try to optimize empirical performance, and this is very important. This is also important to note that is on a given distribution of problem instance, right? So we are trying to optimize an algorithm for something that we will see in the future, that is not very well known right now, right? A new instance. In most cases, this performance can be only estimated, right? So we have parameter values that have an effect on this performance. We have also instances that change this performance. We have some resources that will define what we can get out of this algorithm. And then we also have these other things that are bothering us, right, in optimization, but also in machine learning, for example, when we train models. Stochasticity, and sometimes when we change platforms, algorithms, they change performance too. I will show you, so you can believe me that this is the case, right? So we are going to focus on offline tuning here. So we have two main ways to deal with parameters of algorithms. The first one, and the simpler one, right, I would say, is offline tuning. So before the execution of the algorithm, we set the parameters if we try to find something good. And then online tuning, it's also called control, right? And we are adapting the parameters during the search, right, based on different measures we take, right, about how the optimization process is going. Okay, so what is the normal approach when we are starting to do configuration? Normally it's the manual approach, and I will not go very deep into this, right? But there are many ways in which you can try to attempt to do this manual approach, right? Some people use these values from the literature, and this you can find a lot in papers, right? When you review or read papers, you have these default values of maybe frameworks, then parameters values suggested in the literature, right? So this is a very normal thing. And then sometimes we get this mysterious process in which they try some parameters and they found these values, but not a lot of information about it. And then the next level, right, is to have some systematic, maybe design of experiments, right, to try to find good parameters. So there are several approaches. And I think there are good things and bad things about manual configuration. The good thing is that you can get a lot of information, right? So when you don't know too much the technique that you're working with, like, for example, when you don't know too much your washing machine and you try different things, you start to get to know it, right? It's the same thing with algorithms, right? So you get knowledge, and this is good when you don't have a lot of resources to try something automatic. Bad thing is that this does not provide a lot of flexibility because it's a tedious task, right? So it's something that you do not look forward to do because it's very intense in terms of the time that you have to use, right? And so avoid us to think in new components that we should then later configure and decide if we want to use or not, right? So we are people that we work in automatic configuration. We normally say that we should try to not do so much manual configuration and try to go into manual automatic configuration, where a technique that is designed for this task is actually looking for the best settings of the parameters, right? And this is what I'm going to talk to you about. So these things, and this is what we call the configurator. Right? This is like a black box, and something happens here that will search the parameter space, right? And then it will get some configuration that we can use, right? Parameter space are formalized, so we need to define decision variables, right? That is the parameters we need to search. We have different types of parameters. I'm not going to go really in super detail, but there are some categorical, some order, some numerical. They define different domains too, right? There are different things that they control. Categorical and order, normally they control component selection, what we are going to use or not in our search, right? And then numerical ones, they control normally behavior. Yeah, we're trying to adjust behavior when we are doing this kind of setting, right? And then there are some parameters that are conditional, because since we are adding and removing components, if we want to change the behavior of the parameter of the algorithm, and we need to adjust a component, then the parameters that adjust this component are dependent on this other setting, right? That needs to be active in order to be actually relevant for the configuration, right? So we can have a parameter space like this, right? Some categorical parameters, some order, some real, some integer, right? And some domains associated to this, and this parameter space normally define this hierarchical structure. So this is the solution space, let's say, right, of the configuration problem. What are the things we need to pay attention to, right? As I say, the performance measure, and what we normally want to optimize when we optimize algorithm, we can divide in two, right? Some measures that are based on quality, so we want to have the best performance in terms of solution quality of our algorithm. And then some other measures are resource-based. We want to get the quickest, best solution possible, right? So it's about time, or it's about some other resources. Sometimes if we are in restricted conditions, right, the amount of memory we use for obtaining some kind of solution, right? And we can also penalize this performance measure, indicating some maybe secondary criteria, right? Maybe first time and then memory, for example, and memory gets penalized, right? Instances are very important, and this is what makes the distinction between the configuration problem in machine learning, I think, and in optimization. In optimization, we have the notion of instances, right? So we want our algorithm to be able to generalize in instances. Machine learning, you want also the model to generalize, right? But you have these data sets, right? And it's not very normal to have a lot of them to adjust the model. Normally the models are adjusted to one in particular, maybe two, right? And this is an example of what Gabriela actually does very well, right? And probably she will show us a couple of things. These are local optimal networks of an ILS algorithm. In particular, this is the HealthCon implementation of Lin Kernighan, right? We apply this on a ILS scheme, right? And you can see these are all TSP different instances. Each of these nodes is one local optima, right? And they are connected when the algorithm was able to do a transition between one and another, right? So this example, this instance, it seems to be very connected, well connected for this algorithm, right? So here in the bottom, the lower there is the node, the best is the solution, right? So we can see that most of the local optima are connected to the optimum, right? So this is very nice, and probably the algorithm is using all the intensification mechanism it has, right? But in this instance, these are not connected anymore. You cannot see too much. Maybe in this one you start seeing how it's moving from something very nice for intensification behavior, right, to something that needs some exploration, because these are disconnected. So we need to restart constantly the algorithm. It's not enough intensifying, we need to explore, right? And so even within the same problem, we have different instances that require different behavior from our algorithm. And this means that we need to configure it and adapt it, right? We need to find a good balance. So instances, they should be representative of what we are going to see, right? If we have the case, right, in which we will see, right, when the algorithm is actually being used, different instances like this, we want a configuration that actually is able to generalize across this set, right? It does something good for all these instances. If we have something more heterogeneous, then maybe we can just focus on one type of behavior, right? And this is very different, right? It's not so easy to understand sometimes when you are in industry and you don't have a lot of examples to, and you start really from scratch with a problem, right? So we normally define training and test sets like in machine learning people do, right? Training set just to find a good configuration, and test set to actually test that this configuration actually is able to avoid overtuning, right? I'm not going into much detail about this because I want to show you some other things. There are several algorithm configurators available, right? The one that I'm going to show you is one of them. It's called Iris, but then you have all of these that you can use. Some of them are easier to be found online, right? There is SMAC, for example, and GGA that you can find and download, ParaMLS also. And there are some other ones that are a bit older. There are some other ones that are just algorithms, right, that have been used, like CMIF. And you can normally find them somewhere, right, in a repository and try them out if you want. I'm just going to talk about Iris, right? Iris is a package that we developed with also a lot of other people, right? I can mention Manuel López Ibáñez and Thomas Stutzle, that is the people with I'm worked with more closely, right? It's a open source tool, so you can use them and download them within the R framework. It's shooting multi-platform, and it supports parallel executions. You can run them in clusters. We provide a lot of support for different settings that you can think about, right? What implements inside this package? It's a configurator procedure that will apply some iterated tracing and also combine it with some estimation distribution algorithm, right? So I'm going to go quickly through this because I just want for you to understand more or less what is happening inside Iris. So to understand what are the products of the configurator, right? At the beginning, we do some uniform sampling. We sample some configurations of your algorithm. So each of these is an algorithm with some parameters, and then we have an instance sequence, right? We will start executing each configuration on the instances up to a point in which we decide that there is enough information to make a statistical test, and then we will be able to discard configurations that are statistically not as good as others, basically, right? This is just kind of like an heuristic to decide what is best and what is not, but with some statistical background, right? And then we continue doing this, right, but only with the configurations that are able to survive until we exhaust some budget and we get some elite configurations. which are the survivors of this racing procedure. And these configurations are used to update some estimation distribution, some distributions that are used for sampling the later new configurations. And these distributions are always being more adjusted towards the best values we are finding, right? Again, we do the sampling, right? And we continue for the next iteration, having these configurations that are the ones that are coming from the previous iteration, the lead ones, right? And the new ones, and we start again executing until we get new configurations. We update the sampling distribution and so on and so forth. This is how IRES works in a nutshell, right? So the first thing I want to show you about what IRES can do for you is actually a very simple experimental result, right? This is just 3 algorithms that we can configure, and you can see here, the lower there is the results, the best is the performance of the algorithm. So we have 2 ACO algorithms in which we can optimize the fault settings really easily with IRES, right? This is a multi-objective algorithm. So here we are optimizing the hypervolume, and here the distance to optima. And this is Cplex, which is a well-known framework, right, with several complete techniques. And actually, we can even adjust Cplex. I mean, Cplex is well-known because it has a lot of parameters. This benchmark in particular has 72, which is not the largest we have, but it's a large enough benchmark. And in general, I would say that every time you use Cplex, if you want to get better behavior, you can have it, right? The default settings are very good to generalize over more or less everything, but are not great in anything, right? So it's not difficult to optimize this kind of thing, right? But I want to focus on what actually you can get from configurations besides getting good settings, right? During the design process, IRES actually can help us to understand what is happening with our algorithms, right? And this is an example actually of a work that we did with Alessia Violin, which was at the time a PhD student. She already graduated, right? And she was actually designing this branch and cut and price algorithm with a model that was applied to solve a problem of setting the tolls, right? The tolls of a highway, the price of the toll, right? And we were able to reduce the mean execution time of her algorithm, so was already successful with that, right? But what I'm interested in is actually what happened during this collaboration that we had. So this is what we started, right? Alessia had this model. Yeah, this is the dancing wolf model, right? And she was running her algorithm. So this plot it shows here the time, and this is the number of instances the model was able to solve, right? So this is what she had, the orange line. It was what she had at the beginning, right? This is her manual configuration with this model that was a model that she inherited from another PhD student. We apply IRES and everything was great, right? So the blue line actually was what IRES was able to get from her model. So immediately we can see that the model can solve more instances, right? What it was more interesting is that she was trying to develop these inequalities constraints into the model, right? So we tried it out also, and we tried to optimize it, and we saw that it was more or less not doing nothing, right? So for this model, this component was actually not really important, right? But then she was also working with a second model she was trying to apply, right? And you can see here that she already improved a lot the performance, right? Because this goes from to 60, right? And here we are only to 30. So we were, with this model, we were able to solve many more instances. But then the configuration process was very different in the sense that she was already working a lot with it, right? So her manual configuration was actually rather good. With IRES, so this is the orange one, right? Here. With IRES, we were able to improve it a little bit more, right? We pushed it a bit more. But the inequalities were really not showing any progress for the algorithm, right? And right at the end, actually, the inequalities were actually starting to show some improvement, right? But you needed to run the algorithm for a long time actually to see it. So this collaboration actually helped Alessia to realize that this was not a good approach, which was going to be actually difficult for her if she was doing it manually. But Iris, just with a couple of executions, was able to show her, okay, it seems that this component is not very useful. Maybe you can change it, right? So I'm trying to explain, right, that you can use it to get information easier than if you do manual tuning. Now, also there is the case when we have algorithms that we have been already executing for a while, and then some execution conditions change. For example, we don't have enough time, right? Or the instances became larger, right? So we have less resources. So what happened when the conditions of the execution change for an algorithm, right? And we have these default settings that were actually carefully designed, right? And we know that they work well. And so we try this ACO TSP, and then we reduce the budget that traditionally is used for solving TSP. And then we have also this adaptation of ACO for QIP, and we did the same. We reduced the budget to see what happened with the default settings. And what happened is that for all the algorithms that we have here in this ACO TSP framework, we were able to improve. The only one that actually was a bit resistant to this was Unsystem, which is the most simple algorithm in the ACO family, right? The first one. But the rest of them, the ones that normally are much better, right? Because they exhibit more complex behavior, we were able to improve them much more, right, than Unsystem. This means that every time we change something in the execution conditions or the scenario, we should be paying attention to what happens with our parameter settings. Yeah? It implies that default settings and settings from the literature, these papers that say, okay, we find that these parameter values are very good, right? They are not always applicable to, situations. So what happens when we have a change now in the platform? And this is a bit terrifying. For me, it was terrifying when I did this, right? Because it means that what happens if I change the computer? Because I don't know, maybe my server where I was running the test or the cluster is not available anymore, and I change, right, to a different architecture, maybe some different processor, and that's it. So what we took now is actually a software. It's not anymore an optimization algorithm. It's GCC. And GCC has some optimization options. I don't know if you have ever compiled something, and sometimes you add this -03, 02, yeah? So this is just a set of default settings that the developers of GCC suggest you to get good performance out of GCC. This doesn't mean that always works well. It's just what is suggested that works somehow well in all the cases, right? So we optimize the generation of the executable with GCC of 6 optimization algorithms. There are programs, most of them in C and one in C++. And we optimize the optimization flags of GCC, which are in total 172. And we add, in some cases, right, the mixed parameter space, right, which is 367 between integer and categorical parameters. So it's a large configuration space, a lot of decision variables that are linked to very technical things, right? The size of the registry to define the executable, etc. Yeah? We execute this in 4 different machines, nothing special, they're just different machines. And we compare it to the -03, this is one of the most popular settings. And what we found, right, in all these 6 algorithms, and is that in all of them we were able to have a speed up of the executables that we were generating when we were configuring, right? So the default settings of GCC are okay, but are not fantastic, which in industry makes a difference, right? Because if my algorithm can be 2 times quicker, then it's great, right? And if I can do this very simply by just running a configurator over the thing that is compiling, much better, right? You do it over the weekend, and then when you arrive, you get a good algorithm, right? What is then terrifying, right, is that this speed up is not the same in the different machines. So here we have machine 1, machine 2, machine 4. We have a 1.3 here that we didn't add in this plot, and then machine 5, right? And this is very different sometimes, right? Sometimes you have a very good speed up, and we were able to really have a good speed up here, right? And sometimes something a bit not so great, right? So it really depends on the machine. Sometimes some machines are able to get some speed up in some type of algorithms, and some others not so much. Yeah. So it means every time we change the platform, if we really want to get a high-performing algorithm, we need to pay attention. So this is something that I started off because I had an interesting talk yesterday with Carlos Coelho, and he was saying we need to pay attention to ideas, right? And one of the ideas I have is that actually the configuration procedures are generating a lot of data, right? So we normally think about configurators as techniques that are giving us a good parameter setting, right? But also are generators of data. It's kind of like a sampling procedure, right? But it's not a sampling procedure that is sampling, uniformly. It's sampling focused on the high-performing area of the parameter space, because we are trying to optimize, right? And so we can use them to understand what is happening in our parameter landscape, and therefore understanding our algorithms, right? So we should be using this data that we can generate for free, right? Because we are just trying to configure to actually analyze things, right? And so we developed this package that we are soon going to have it as an official R package, where we provide some plots just to start talking about this, right? And normally what you would want to see first, without thinking too much, is what is the performance of the elite configuration. So IRES gives you as output a set of elite configurations that are not statistically different between them, right? They are, we could not decide which one is better, so this is the set of elite configuration. And the one that is in color here, so this is the distance to optima, in this case. Each one of these one is an elite configuration. The one that IRES thinks is better because it has a better mean, because remember, all of them are the same statistically, right? Or at least not, there is no evidence that there are different, is 809, right? But we can then check testing data, right? Because this one here before, I forgot to mention, this is training data, right? This is what IRES is saying. We can do testing data, which IRES actually does, and then we can figure out that actually on testing, right, this is not so good anymore. There is one that appears to be a bit better. Maybe not statistically different yet, but if we have to choose, right, we choose this one, right? It's a no-brainer, right? So we can start analyzing these things, right? We have information there, so we can check this kind of thing. Then we can understand what is happening inside the configuration procedure and how it's moving through the performance space, if you like, right? So this is the last iteration, and here we have the last elite configuration, but then we have a bunch of other configurations that were showing to be good at different points, so during the iteration, right? We can try to understand also the instances, right? Like why here on the back, right, we have these two configurations, that 809 that was appearing to be good and then was not so good compared to the 808, right? And we can try to compare them and try to understand each point here is an instance, an execution, right? Why 808 is much better. And we can discover here that there is a set of instances that apparently is very easy for 808, right? So when we have instances like this one, then there is no question that we should get this kind of configuration. But for these other ones, the ones in the bottom, it's not very good, 808. Actually, it's very bad, right? So we should have this kind of configuration, right? This is very useful, because if you have an instance with certain characteristic, then you have choices, right? We can also understand how parameters are related, right? And we can see how values are normally selected. The more the lines, each line is a configuration here, and the darker the line, it will show that is a good configuration. So the more dark configurations are the best, because in IRES we try to increase the the precision of the performance estimation when a configuration is good, right? So this is why we see it like this. So we can see, right, that there is some relationship, for example, between alpha and beta values, right? So these ones are around here, and then rho is always on this side, right? And it's always combined like this. So we can start getting parameters. We can also see what happens here with the sampling distribution and understand where, right, IRS is thinking that the best values are centered, right? In this case, for example, for a COTSP, we know that the algorithm that appears to have the best performance is ACS, right? And it has a higher probability to be selected. This is a frequency actually of the sampling, and then we can derive, right, the distribution for the numerical parameters, right? And we can see where the sampling was centered, right? We can understand where we should be looking at. Yeah, here we have the close-up, for example, for parameter beta. We see that was sampled here more in this area, around 5. So probably good values are around there, right? We can see also how this sampling evolved to understand how the configurator actually focused on different areas of the parameter space. There is something I didn't mention, but IRS actually has a population of models, actually. It's not just one model that we are updating. We are updating a full set of models. And so we have different models, and the result of the sampling with these models is this, right? So this is an aggregation. Each iteration, we have some kind of agreement within this model where there is this area that is interesting, right? And they can disagree too. So we could see different places, like in here, right, when we are sampling around this area, and then also around this other area. We can also see how the configuration process is evolving, right? And this is another package. It's called ACVs. We made this in collaboration with Marcelo Sousa and Marcus Reed. And this is interesting just to see, because we can see how the benchmarks are different. We can study how they are different. And in this case, we have here an instance that is actually not providing any kind of information. If you see, each of these points is the execution of a configuration in an instance, and the color, it shows the instance, right? So each point is a configuration, and the color is the. And so here, the configuration, the instance that is here in the gray color, it's not doing anything, right? So we should remove this configuration from the configuration, in this instance from the configuration procedure, because it's not giving us any kind of information. It appears to be very easy, because even at the beginning of the configuration process, right, this is a number of evaluations in the IRS execution, even at the initial stage, we are able to solve it well, right? So this helps us to design a good scenario for configuring an algorithm, right? And we can see how different are benchmarks. Right? This is a COTSP, so this is what we always choose to show, because we know the algorithm really well, so we know what to expect, right? But this is a different one. This is, for example, a SAT solver. It's called Sphere, and this is very different, right? In here, this is a much difficult benchmark. That's the first thing. And then we can see that optimization is very, very difficult. It takes time. This line here is the mean, right? So we are really reducing little by little the optimization of the performance, right? Making it better. We can also visualize what happens when we have heterogeneous benchmarks. So heterogeneous benchmark I call when some configurations are really good for one type of instance and very bad for another type of instance. So you need to find something that generalizes. Sometimes you want to know this because you are not aware that your benchmark is heterogeneous, right? And this is an example. Here we have on the bottom, so the second half of the matrix, we have a set of instances here on the y-axis that was used for training, right? So they were used in configuration, right? So we know that the best configurations here, this is the list of configurations, are these ones around here. So the greener the color, the better is the rank of the configuration in the instance, right? And the second half of the matrix, here the upper part, we have a set of instances that were used only for testing. So these are instances that are different from training, and they are chosen because they are really different, right, of this algorithm. And we can see that here is very different the story. So this configuration was really bad in terms of training, right? It has the worst rank here, so it has the red code. But then for testing, it's super good, right? So it's difficult to get an agreement. We have a heterogeneous set, right? So it's difficult to find something that is good, and then we get this kind of thing, right? When testing and training shows different things, and we need to be able to balance this type of configurations of instances when we are configuring, right? So we can visualize this and understand what is happening just with the data that we are getting from configuration, right? From the configuration process, right? Okay, so the next thing is I would like to discuss with you, right, is that we are generating all this information here when we are configuring, and this is information that is somehow biased towards an area of the parameter space. And then we can just take this information and pass it to a model, right? So we can train a model and try to predict performance. See, and this has been done already. There is a configurator that is called SMAC that actually has a random forest model inside. So you can predict performance, and this is okay, but actually we can use also random forest to estimate importance of parameters, which is also another type of information that is really useful, right? So how can we measure importance when we are using random forest models? So we can use, right, the increase of the error, right, the mean square error, or maybe we can use as an importance measure how many nodes in the trees have been used, right, have been using this variable to do the split. Or we can count, for example, how many times a variable is used in the first split, in the roots node. Or we can use this measure that for me is very interesting. It's called the mean minimum depth of a variable to measure how deep in the trees this variable is used, right? So how useful is at the very beginning to decide performance, basically, right? To classify the performance. So all these things we can use as some kind of like an heuristic to understand, and I will show you some plots, because this is things that we are just trying to put together. So this is not published, so it's between us and the internet, right? So this plot is showing here on the bottom the parameters of an algorithm, and these are 5 executions of iris. So each color will show 5 executions of the algorithm, right? And these are what we can see in terms of what it is the importance of these parameters in order to predict performance, right? We are trying to build a model to predict performance. And we can see here for this algorithm that the higher, right, importance, if we want to say here, normally is achieved by the local search parameter. So this is the one that is affecting more or deciding more, let's say, the performance of the model. And this is very reasonable. For us that we know the algorithm, we know already that local search is the most important parameter, and it should be set really quickly during the search, right? Because we know that the best local search is going to always give you better results. And then next, we have these other ones that are more or less at the same degree of importance. And these are all related to local search and to this heuristic, the don't look bits, right? And we know also that they are very important, right? We know that this NLS will depend on the local search, right? So it's kind of like a secondary kind of importance, right? So we can see this. And also here we have the instance. So we are seeing here that the instance is also very important to predict. I don't know if you see very well. It's a bit difficult to see in this plot because the letter is a bit small. But I can give you then the sources if you want. Actually, I have a little website in Shiny App, so you can have a look with this plot. So this plot actually will show us then what happens when we change to another measure. This is a mean depth of the variables, and this is inverted. So normally, the smaller the depth, right, then the more important it is because it's closer to the root. So this I inverted. So now the higher the number is better, or the high end in the plot is better, right? And we can see here, right, that we have a very different importance landscape. It changes a lot, right? And some variables are chosen to be used rather early, and this is the case of local search, right? But also the case of instances here, right? And some other ones. So this is showing us somehow a different way of assessing importance, I think. Somehow a different classification of importance. And this depends actually on how the domain is affecting the performance of the algorithm, right? If I need to set just one value, if I need to set a range of values, right? And the random forest model is able to pick up really well because they are actually made for this, right? So we can assess this, and then we can just maybe plot these kind of things and start to understanding what is important. For example, here we have a local search, the local search parameter here again, and we have a parameter that has a high importance in terms of error, a high importance in terms of mean depth, but actually a very low count of usage in terms of number of nodes, right? This means that this parameter needs to be set to one value, right? Very, very, very simply, we just need one split in order to decide what is the performance, right? Having a really big effect on the model. This is one type of importance, right? And then we have some other parameters, right? Like, let's say, this one around here, right? The instance, in which apparently we use it a lot, right? So we need to make a lot of splits. This is not a parameter, right? But the instance we use also as a source of variability in performance, right? So it sounds like something that we need to analyze in this case. And then we have all of them, right, somehow high, which means that we are using it a lot as a split, but also it has a big impact on performance directly, right, in the performance of the model. Yeah? And don't look bits, right, that has something in the middle. Right? So we could start trying to analyze what is happening with these measures and trying to understand what we need to pay attention regarding these parameters. And we can plot them in this way, right, and understand, for example, local search, like I said, has a very small mean depth, right, and a very low count of numbers. So this is one type of parameter. So in this area, we will get these parameters that need to be set to a particular value in the domain, or a very narrow value, right? And then we have these other ones like instance that have a very small mean depth, right? But then a high count of number of nodes, right? And these are parameters that normally we need to really try to understand where in the domain they are, and they depend normally of other parameters, right? We need to investigate maybe more about their interaction, right? Another interesting thing, and this is why we go through this, right, is that we can, the mean minimum depth is able actually to offer us an estimation of interactions between parameters. And this is very difficult to actually assess in algorithms, right? Because some components, they might interact. We know that some components activate some other parameters, right? But sometimes we have interaction between components that is not really easy to pick up, right? And this is important because if we want to get to know the algorithm, right, we should be aware of this, right? So, we can actually estimate this using the minimum depth, and if we combine them, right, to have the combined minimum depth. And actually this worked quite well. This is just preliminary, yeah, so still we don't have the right tool. But we can see here that out of these benchmarks we have, this method is able to pick up that, for instance, algorithm and instance are interacting. So basically, if you have a different instance, then maybe you need to set a different algorithm in this case, right? So this is signaling us that we have maybe an heterogeneous benchmark, which means that we need to pay attention to what we are using when we have an idea of what type of instances we are solving, right? And here we have also interactions that make a lot of sense for us, right? So algorithm also interacts with the number of ants. Depending on the algorithm, we need to decide how many ants this ACO algorithm is using. And also the ants and local. The last thing, and I know I'm late, so I will show you really, really quickly. It's this idea of configurators and design, right? So the design process is iterative and is a bit tedious, right? It requires you to be constantly trying things and see how it's performance. And then on automatic algorithm configuration, we say that the next step is automatic design. So postpone all the design decisions for the execution time and make all these frameworks that are really full of components that you can use and instantiate whenever you need to, right? So what happened, right, is automatic design in general is challenging because it has all these problems, right? It's expensive, it's time consuming, and even though we have a lot of computation capacity right now, still it's very heavy, right? And representation of the design spaces is normally also very important in this sense. And I will show you two examples. The first thing I will show you is something that we are working now with a student. We made a framework in which we didn't do anything new, right? We take all these papers from literature in CVRP, so vehicle routing. There is a lot of research, right? It's a problem with a lot of applications, so you get a lot of different algorithms every time published. So we took a couple of them that they were somehow good, right? And we implement them in a framework, right? This framework then can be instantiated through this command line, and we can take this component space, right, and define some grammar in order to combine them, right? So in this way, we can say, for example, an ILS will be a local search, right, a termination criteria, a perturbation, and an acceptance criteria. And a local search will be, for example, either a first improvement, a best improvement, a taboo search, another ILS, or an empty local search, for example, right? Which means that we can start nesting algorithms, right? This, of course, we of nesting. And we can search actually now not only parameter settings, but also algorithmic structure, right? We can create new algorithms, basically. And so we did this, and this is very preliminary. We didn't do anything crazy, right? So we implement in the framework these algorithms that are here. So this is an iterated variable neighborhood descent, some simulated annealing, some taboo search with different initialization mechanisms. So all these ones that are here. And we have this algorithm that we know is very good, that is a VNS, right? This one we didn't implement it. We used it just to compare, right? We implemented it on the side. And this is something that was generated using this process in which we are instantiating this algorithmic structure automatically using IRES, a configurator, because you can translate grammar to parameter spaces very, very simply, right? There is a process that you can do it. And it's very interesting, right? Because we were able to improve all the algorithms we were using as base with nothing new, huh? We didn't do anything new. We didn't talk too much about it. We just see it, we program it, we run it into IRES, and then bam, we get a new algorithm. That is actually, it's similar to this one, so it's an iterated variable neighborhood descent, but it has a perturbation that was different. It was a sequential perturbation that was joining some movements one after other, right? Some perturbation operator, and then it applies also a simulated annealing criteria, because IRES found that this was working well, right? So this would be like if I was going for the pragmatic thing, then I would tell my student, "Oh, let's publish this one," right? And we say we design it, right? This is very simple, right? And having this kind of mechanisms, right, this framework, will allow to have algorithms designed effectively for ad hoc situations, right? Very simply, which is kind of like a democratization of optimization. One of the things that is difficult about optimization is that, machine learning, there is a lot of standardization. So now I can go without knowing anything about machine learning. I download this library and I have my neural network without too much thought, right? I follow a tutorial and there you go. But in optimization, it's a bit more difficult. We are a bit more reluctant to make so much standardization, and this is difficult then for people in industry, for example, to make effective algorithms. And these kind of things it shows that actually should not be that difficult. You can get a very good algorithm with things that are there already, right? And the last example really quickly I will show you, is that we were exploring this benchmark that is called NASBench 101 at this time, which is a benchmark that supports the design or aims at supporting the design in neural architecture search, right? So it has a sampling of neural architecture, right? Some different architectures that were tested, right? And then they were evaluated and put together in this nice benchmark that you can use, right? And then the architecture is defined by the stack cell. This is just defined by the developers of this benchmark, right? So we're not going to go. The cells are modeled like a direct acyclic graph, right? And they represent each node and a layer of the network, right? What is this NASBench benchmark characteristic, right? They will sample the performance of these architectures. They define that there will be up to 5 layers in this benchmark, right? So this is the benchmark defined, right? There are some different stopping criteria in TPU time, right? There is evaluation in terms of training, validation, and test accuracy, and some repetitions. 3, which is they defined that was enough for the benchmark, right? And solutions when configuring, because this is originally is not what we did. We just tested it and see what was happening, right? They define the configuration space as an adjacency matrix with a list of nodes that are the types of the layers, right? So something a bit like this. We have this stack, right, with different cells. This is what the benchmark looks like conceptually, right? And each of these cells is kind of like this, right? So different layers with different types of networks there. Yeah. Okay, so this is what we get when with the originally proposed NAS benchmark, right? We have a fixed number of nodes, and these are 3 different configurators. This is SMAC, this is regularized evolution, and this is IRES, right? And more or less, they have some agreement. The problem with this, we started realizing when we were working with the benchmark, is that they define fixing 5 nodes of network. But then when we translate this parameter space to architecture space, they were not always the 5 layers active. So we had this problem of discrepancy between search space and actual solution in the architecture space, which is very bad because then the configurator does not know. It can get confused, right? Any kind of procedure that is trying to optimize something that is not exactly what we are optimizing will get into trouble. And we actually changed this very simply, right, in the definition of the benchmark, and we figured out that actually most of the time, the 5 layers were not needed, right? So this is an example, I think is an example of why representation is so important, right? We need parameter spaces to be well represented, and design spaces, especially in these kind of things when we are moving towards more complex things like neural architecture, should be well designed for complexity, like we did with the grammar, right? The grammar was complex enough, and it can show us, right, very well from parameter space to design space what we are doing. The configurator knows. But in this case, for this benchmark, was not the case, right? So it's important to have this, and this is a problem that is not only in optimization, it's a problem also in machine learning, and I think it has been detected also by people in machine learning, right? The types of parameters that they're using for optimizing this kind of thing. But this is the performance, and I will not go into this, so I will just finish because I'm super late. So what you should get from this talk is that you should always configure. It's better configuring even manually than nothing, right? try not to submit your papers, right, with this esoterical kind of process in which we test some parameter values, right? So try to maybe use an automatic configurator and say, okay, we delegate this process to an automatic tool and we got this configuration, right? It's much better than just say we test a couple of values and maybe we got a good configuration, who knows, right? Also, keep in mind that configuration, automatic or not, will give you a lot of information, so you should always be positive about this, right? And it can also help you to design your algorithm if you're trying to build one. And also I want to leave in your minds, right, the fact that we are moving towards automated design, right? And we can show very simply, without doing too much, that automated design is possible. And you don't need to be an expert to get really good algorithms if you have a framework available. So we should try to move in optimization to actually develop frameworks in which we are able to combine these components. Because we have a lot of research. There are very nice techniques, and now we have the computational power to actually design things automatically. Okay? So yes, this is what I wanted to tell you. So now you can ask some questions.
Thank you very much for your very nice talk. Are there any questions? Yes.
I have a couple of questions, Leslie. One is about the homogeneous and heterogeneous, instances. So it seems to be an obsession of finding a single parameter setting. I'm wondering whether if you have an heterogeneous set of instances, maybe it's better for the algorithm to provide two parameter sets, and if you can kind of automatically kind of separate the instances and provide more than one. Is it part of the idea?
So this is what we have talked several times with Gabriela, and I think what she does with the fitness landscape is actually what we need. We need to figure out a way to use it, right? It's not easy to assess, right, how heterogeneous is an instance, right? And it's an instance. So now we are normally using some concordance correlation coefficient to understand whether the instances are agreeing between them in terms of performance, and we can get an indication, right? So this is somehow heterogeneous. We know that we have some heterogeneous benchmarks because we have run these algorithms hundreds of times. We know, but it's just because of our experience. We would like to have some heuristic method that will tell us, raise the flag and say, hey, this is heterogeneous, right? Once you understand that something is heterogeneous, then the next thing is understanding which instances are similar to which, right? Some kind of clustering, right? And for this, we need to have some indicators, right? Something that we can measure and we compare, right? And fitness landscape analysis is actually providing some kind of intuition about this, right? So the next step is to involve this kind of techniques into a configuration procedure. So you could say, okay, I need a configurator that generalizes, a configuration that generalizes, but also in some cases, I might not really know that my scenario is heterogeneous. So I can suggest, hey, you have maybe this configuration that we know it generalizes somehow well, right? But you can use also this set of configurations associated to different instances if you want to get high performance for this kind of instance, right? And just leave the user with the decision there. We have the information right now to actually do this analysis. What we are missing is the tools, right, to actually do it. So that's why eventually I think we will merge somehow this thing. Yeah. We are on the way. So we are aware of the problem. We know what we have to do. We don't know how to do it.
So thank you very much. Very interesting work and very useful for the ones who are in industry, and it's really important. I was wondering in this support process for the decision makers in the end, if we are not limiting them a lot, and the question goes in the direction of this very discretionary process in which, for example, in multimodal decisions, how much freedom the decision maker would have if you select everything for him?
Well, that's a good question. The first question I would have is, does the decision maker want to have these degrees of freedom or just want a choice, right? So if you are in the business, let's say, of developing algorithms, if you are a researcher, for example, you want to have control of this, right? Because you want to know what is happening. And so I envision this like a support tool in which I wish it would be somehow interactive, right? So the designer will be saying, okay, look, it looks like you have this kind of situation, for example, with this component, right? It seems to be interacting with B. Why you don't focus, right, your analysis on this and then you move on, right? This would be good, really, to specialize things, right? When the users are very, very interested in what's happening, really inside the technique. But there are some cases, for example, in industry, which normally they just want something that works. This is something that I learned not so many years ago. I'm kind of young in what I'm doing, right? I finished my PhD not so long ago. But I've been in contact with some people in industry, and I realized they don't care so much as we in research, right? In high performance, right? They want something that works. They work relatively well, right? And so, and of course it should not take a lot of resources too. So they want that the cheaper the better, right? And so for them, if you have a logistic problem that you will solve every week, right? And you can get over the weekend, for example, an optimized algorithm for certain kind of things that you know is coming next week. That would be great for them. They don't want to really understand too much. They just want the tool, right? And so in academia, we have the components, right? We just need to make them work well. And sometimes the developing process, they take a while, right? And there is people sometimes in departments, in companies doing this, and they take time. And this is good, right? Because they know, let's say, the business and what they are doing. But then we can provide these tools that actually can assist them to generate something that works. In the meantime, they can use their time to develop new things, right? And to try to push the state of the art instead of having this very repetitive task to try to find something that works somewhere well, right? So there are two things, I think, right? People that want to know really well and then should be assisted, but in a different way with more control. And there are some other things that are really, it's more pragmatic, right? We want something working. We are not making the effort to provide this, I call it democracy, right? So it's a more democratic optimization. Allow everybody to do optimization without actually knowing too much what is happening inside there.
Thank you very much.
It's more a comment than a question. I think that this approach that you're using for design could also be helpful to understand which components of an algorithm are important, and because many times you have to compare with an algorithm that has like 10 components, and the other algorithm works, present better results, and you do not understand what is the key component for doing that, and I think that this will help us to understand better very good algorithms and to approach those ideas to other kind of algorithms. So maybe you I don't know, that example that you say with the perturbation, maybe that perturbation in another algorithm the author didn't consider because he didn't have the idea, and the key factor is the perturbation and not the rest of the algorithm.
Yeah. So that's actually a very good point. So right now, right, we are kind of pushed sometimes to publish rather quickly, right, in the field maybe, and so there is less analysis to what is happening, like what is the behavior of the search that actually is contributing more to get high performance, right? What is actually working for certain kind of instances or certain kind of problems. And so that makes us just maybe trying things and then, it works, right? And then we leave the analysis for later, and this comes maybe later that we realize, okay, this component might be important, right? Like for us in ACO-TSP, we know local search, it's a key component, right? But this we know because we have executed the algorithm many times, right? And we know by experience. And so it would be great to have something that is that requires less from the person in terms of time, right? Because I think one of the barriers that there is now is that to understand what component actually is doing the job, like is carrying the heavy weight in the search procedure, right? It means that you have to execute a lot of experiments, right? And this requires time, requires planning, right? But if you have a tool that is able to give you this information somehow automatically, and then provides all these other tools to analyze it and kind of digest it for you, it's great. I think for students, above all, it's fantastic. It would be great for them to actually try things and maybe go crazy. A lot of students, when I do meta-heuristic, they have ideas, right? Why I don't do these kind of things? And then, okay, you can try them, but then you don't know if they work, and if they work, why they work. Are they similar to other things, for example? Another interesting thing is knowing when components are exchangeable, right? So you can put one or another. So there is a lot of things that would be nicer if this thing would be more available and also a bit more, let's say, organized, right? Standardized. So yeah, I hope people use things.
Okay. We will have just one last question because we must then move on to the next session.
Okay, congratulations for your work, and thanks for enlightening talk. But when you automatize this kind of process, you kind of take out the responsibility of the clients, and they expect to work every time they use it.
Yeah.
What the degree of confidence that you can provide to your clients?
So let's say that automatic design is kind of young, right? It's still, because there is a barrier. You have to have first the framework, right? And then you have to give these degrees of freedom in which you have to be able to add the flexibility of having full freedom in terms of algorithmic structure, right? So it's not anymore selecting things and put them in the puzzle. It's actually imagining a whole structure again. So this requires some work, technical work, right, to get this straight. So there is not a lot of things that I've seen of automatic design, but there is a bunch of work. I mean, a couple of them that you can see them in the literature that show that it's actually not difficult to do design if you have this kind of things, right? There is a work that is very nice of Federico Bagnozzi, in which he took all the components he found on the literature on a permutation flowshop, which is a problem that has a lot of applications too. And he was able, after a couple of years of working in the algorithm and doing the thing, to beat every state-of-the-art algorithm with something that he did not design because it was designed automatically. He just implemented things on a framework, right? So it means that we might be able to get even better algorithms that we have currently now. Because the procedure, right, the search, the configurator is not bounded by your ideas, right? He will just try things, right? It will go crazy and mix, like I say, some simulated annealing with some strange perturbation that is linked somehow in a chain, right? He will try everything, right? It does not have any bounds regarding this, right? So I think the evidence, right, shows that it's not so difficult, right? It's possible to do this in all problems? Probably no, right? Some problems are a bit more strange, right? They're not very well studied. But what I've seen, right, and what I did with my students, it was really, we are not experts on BRP. We had not designed any other algorithm before for BRP, and we got an algorithm that was better than any other thing we found there that we added in the literature, from the literature, right? So my impression is that it's not so difficult, right? Of course, there would be some exceptions, but I think we can be quite confident that this could work in most of the cases, at least for well-known problems.
Okay. Thank you very much. Well, just thank you again.
Thank you. Thank you very much.
For coming. Montevideo.
Thank you
being
for the
present
invitation.
here.
I'm happy to be here. First time in Montevideo.
Thank you a lot. Thanks. Okay, well, now we move on to the next session. We move now on to the next session. We ask the speakers, I don't know, who will present the first talk. Gonzalo, Berger. Sorry. Just okay. Just we start. Okay, Gonzalo. Everything's ready.
Start fine.
Wait a second. Yes. Just wait a second. I just take advantage of the time. The authors of the second and third paper have already charged their PDF at the technical site. Tenemos las presentaciones de segundo y tercero. Ok. Está todo. Perfecto. Okay. Ready to go.
Okay. Thank you. Is that fine? Fine. Thank you. Hello everyone. Good morning. My name is Gonzalo Berger. It's a pleasure to be here presenting our work alongside Tatiana, Luis, and Ayala. As you can see by the title, it's basically I will be presenting a tool for generating question-answer exercises using transformers-based models. Just to give you a bit of context very briefly, this is a continuous line of work which stems from a 2019 undergraduate thesis by Martín Morón and Joaquín Scocosa, which had the same objective of generating a tool that helped to assist the teaching of English by generating questions and answers automatically. The main difference is that it used a rule-based approach where each type of question was generated by a different set of rules, and they also generated a corpus of the desired level of A1 and A2 levels of English. So our work was trying to give an alternative to that rule-based approach, and in where we used a neural approach. And the two main phases of our work are the answer selection phase and the question generation phase. And our input is a text from which we want to generate our questions and answer pairs. So we first have to generate a set of candidate answers. That's where the answer selection phase comes in. That phase is rule-based. I will be expanding on it on a bit. And then the question generation phase is the neural part, where we take the set of candidate answers and the input text also, and generate the questions based on that set of possible answers. Then, as you can see in the image, there's a pipeline where there are 4 phases. The other 2 phases are a pre-processing and post-processing phase that we added after observing some errors and some things that we thought could be fixed by adding a stage before and after the the two main phases. I will be expanding on it now. So the pre-processing stage is mainly because we observed that the answers selected and also the questions generated sometimes have words like you can see there, like he or what does he tell her, where it would be desirable to instead, in this example, have the answer be Matthew. It's just that since we take spans of text as answers, we here the model took he as an answer, and of course that we would like to have Matthew as an answer. And in the other case, it's the question, where the problematic part, where we have a question that, again, we would like to have Haley as her and the doctor as he. And for that phase, we use coreference resolution. This is the preprocessing stage. We use the Allen NLP library. So in this case, we take the input text, and after the coreference resolution stage, we transform the text, and the word he is substituted by Matthew. So now when our pipeline selects the answers, it instead of selecting he, it selects Matthew, and in the same in the other question. In the answer selection phase, our goal is to extract a set of candidate answers based on the input text, and we use semantic rock labeling for that. We also use Allen NLP for that, and using prop bank notation. Sorry, prop bank notation is specified here below. It's a set of labels that each semantic role is labeled by a different label. So we then take a possible answer as if it coincides with one of the labels that we want to include as candidate answers. So, for example, if we say we only take answers that are labeled as ARC0 or ARC1, we would have Mark, a jacket, and he as candidate answers. Then, in the question generation phase, our goal is to generate questions based on our set of answers previously selected from the input text. We use a model as baseline. It's available in Heinz phase. It's a model already pre-trained over SQL, and we fine-tune that model over NewsQA, QA, which is another QA dataset, and another model fine-tuning over NewsQA and also SQL. Then the post-processing stage, was added after noting some malformations in generated questions. For example, we have some questions generated with multiple question signs, and some questions where the model kept generating text after the first question sign. So then what we did is introduce a set of rules after the question generation phase, where we eliminate those kind of errors. We also formulated and generated a small corpus, just as in the 2019 undergraduate thesis I mentioned. We extracted text from the web page, from the web, and then for each text we annotated question-answer pairs. So, for example, in this text, if we select Shaq as an answer, what question could be asked where Shaq is the answer, and that question would be who was hungry, for example. And those question-answer pairs were annotated, and then in that way we generate the corpus. And of course, the answer is always a span of text. That's why we select the answer and generate the question. Here is just a graph of of the distribution of the corpus. I think it's a bit pixelated. So the blue one is the corpus we elaborated now. The yellow one, I believe, is the previous the previous corpus already pre-existed, the pre-existing corpus of the 2019 undergraduate thesis. And then the green bars are the combined one. We merged both corpuses so as to have a bigger data set to work with. And as you can see, it's not a huge data set, but it serves its purposes for our evaluation needs. And just to present some results, here is the results of our model. This is the question generation phase as isolated, and the corrects column indicates whether the coreference resolution stage is applied or not. So that's the thing I want to remark the most, I think. As you can see, when the coreference resolution stage is applied, results are greatly improved. So that's one thing we observed, and again, that's what I wanted to remark the most. Then some comparison to related works. Here we have the baseline that we took and the two models that we trained, and some works that also evaluated over squad. I'm sorry, I didn't say that. This is comparison over squad, also for the question generation phase isolated. And as you can see, the results are very similar or in a quite acceptable range. Some works are quite better, but I want to note that squad is a dataset of higher level questions than we want to generate. So in the next evaluation, we evaluate over. Now we evaluate the entire pipeline, so not only the question generation phase, and over our dataset. And here, pipeline 1 uses the NewsQA fine-tuned model, and pipeline 2 uses the squad and NewsQA fine-tuned model. As you can see, both models generate pretty much the same amount of question and answer pairs. And our automatic evaluation gives not particularly good results, but after a manual evaluation where the questions and answer pairs generated were observed, they were observed, and if it was an acceptable question answer pair, it was tagged as okay. If it was wrong, it was tagged as wrong, and strange is it was tagged if it could be accepted, but it was worded in a strange way. So in that evaluation, we see that maybe the automatic evaluation is a bit strict, and I think I didn't mention we use exact match here to compare. So what we can say about the other evaluation is that a lot of questions that are generated but are not exactly the same are still okay questions. It's just that they were not present in the reference set. Then an example use of the platform, I don't think you can see very much there, but this is a platform where the tool is integrated. It has a wide variety of things, not only this tool. And particularly to our tool, as I said, the only input is the text. And based on that text, we generate question answer pairs. I will try to mark because I don't think you can see very well, but based on that text, it generates a wide variety of questions here. And so in this case, the teacher would have access to this part, and they could select which questions to keep, which to discard. They can also modify questions and also add possible other answers. So, for example, since we consider only span of answers as span of text, maybe a possible answer would be to add another word that it's maybe not part of the span, but is also correct, so that in here you can add it as a possible answer, and that. And also I don't think you can see it, but this last one is the problematic one of the list, let's say. And in that case, what happens is the coreference resolution stage solved a coreference, but it referenced the wrong main subject, let's say. So in this case, instead of one name, I think it's Matthew, it puts Sean or something like that. So it mistakes the names in that case. But as we've seen, before, the coreference resolution stage is greatly beneficial for our model. So even though it introduces some errors like that, it still compensates with other things that it solves. And then just to conclude, what we did was the development of a tool for English teaching. The idea is for this to be used in that way as a tool for assisting teachers to generate tests and question answers for tests automatically. We also generated a new corpus that we then mixed with the pre-existing one, making a bigger corpus in general of the level we want to evaluate. And then we also have continued our line of work. As I mentioned, this stems from a pre-existing work. So we were able to implement an alternative to the rule-based approach that already existed. And some lines of future work I wanted to mention. We as you've seen, we only experimented with T5 based models, so it would be desirable to also explore other models such as BERT. We also would like to expand the corpus even more, the specific corpus of our level, since it's small and since we use it to evaluate, it's okay, but it would be desirable to have a bigger corpus to at least train in the level that we want. And that's the following point: train over a corpus that's more aligned with the level that we want to evaluate, and also explore different answer selection approaches. As I mentioned, we use semantic role labeling, but we could try different combinations with the model and see what works best. And that will be all. Thank you for listening, and I hope it was interesting.
Thank you, Gonzalo, for the presentation. Are there any questions? Okay, I have a general question. How do you feel the interaction of these kind of tools with the actual teachers is? Are teachers really happy to have this kind of tools to help them? Or do they feel somehow menaced?
Okay. Yes, I think you're saying if it could be somewhat intrusive, for example. Yes, it's definitely something to note. if used correctly, the idea would be to use it in places, for example, rural schools or places where not every time a teacher can be present, an English teacher. So in those cases, the idea would be to have tools like this. Obviously, as I mentioned, this is a continuous line of work. So the idea would be to keep improving it. And in that case, it would be used correctly, as I said. It will be fine as a way to assist in teaching. Of course, it would be intrusive if we use it as a way of replacing the teachers or the people that help in teaching English. So no, that basically we like every tool, if we use it correctly, I think it's beneficial, and not using it in an intrusive way like that.
Okay. And as future work, you are planning to work with other languages? Which languages do you plan to start with?
With other languages, like other than English, for example?
Yes. I understood that was one of the lines.
Yes. It would be good to expand into other languages. I think the English is the predominant language that is taught at least in Uruguay, but maybe in some of the other languages like Portuguese, it could be implemented also. I think I'm guessing, but I think it's probably the second most taught language. And yes, of course, it would be desired to expand on other languages to also help the teaching of those languages.
One problem there is the availability of the corpuses, no?
Yes, of course. In English, there's a whole lot of information, more than any other language, I think. But yes, in that case, it would be maybe more difficult to gather information, to gather enough information to do the same work. But it would be possible also, yes.
Okay. Thank you a lot.
Thank you.
Any other question? No? Well, thanks again.
Thank you, everyone.
Mm-hmm.
Okay. We move on to the next presentation. We receive João Enrique de Medeiros Delgado, who will be presenting his work, Autoencoder Performance Analysis with Adaptive and Trainable Activation Function to Compress Images. Please.
Okay, good morning. First, I'm nervous because English is not my first language. It's not so good to speaking, but the focus is the content. And my name is João, and I will present to you the Autoencoder Performance Analysis with Adaptive and Trainable Activation Function to Compress Image. Okay, in all our artificial neural network, there was a concept of the neuron, artificial neuron. Here in this image, we see the represent of the circles, and And the neuron is a information processing unit, a fundamental part of the operation of the entire network. Here we see the schematic representation of neuron, and the neuron has one of the basic elements that make up the neuron, the activation function. Sorry. And the role of the activation function is to define how the weighted sum of the input weights together with the bias will be transformed to output, neural outputs. And we have a lot of activation functions. We see here the classical activation functions, sigmoid, tan, and relu. But there are a lot of interest in identify new activation functions. In recent years, we have particular interest in new activation functions that can contribute to increased network performance. And this kind of activation functions has characteristics who have height being trained together with the network. Okay, in particular, we see the GLN. GLN is an adaptive and trainable activation function. And here we see the schematic representation of the global local neuron. GLN combines two mathematical functions in a complementary way given by this equation here. And we have the two components. One component is a global component and the local component. For specific global local neuron, we have the alpha weights that is being trained in the network. And if the alpha has the value 1, the GLN chooses the global component of this activation function. And if the alpha weight has the 0 value, the GLN has the local component the most. But alpha is between 0 and 1, and the value can be any one of this value. Okay, and for this study, we see we intend to evaluate the performance of the GLN employed in the standard autoencoder network to compress images. And an autoencoder is a self-supervised learning, and we see more details. And one autoencoder has the same number of the input layers, with the same number of the output layers. And between the input layers and output layers, we have the intermediate layers. And in the middle, we have the bottleneck layers that has the fewest value of the number of neurons, the standard autoencoder. And an autoencoder has two submodels. The first submodel is an encoder, represented here in highlights. And the other submodel or the decoder that is from the bottleneck and to the output layer. Okay, let's see the experimental results and methodology. First, the dataset used. We use the CIFAR-10. CIFAR-10 has 6,000 color image divided in 10 categories. These categories, and each image has 32 by 32 pixels. Each image has 30 layers, 3 RGB layers, green, red, and blue. And okay, now the process. As I said, our intent is to evaluate the performance of GLN in an autoencoder. And for this, we divide the process in two stages. The first stage is training an MLP autoencoder neural network. We use 50,000 images for that. And the second stage is used to 10 images to compress an autoencoder and use in WRN, wide residual network, and SVM, support or vector machine for classification. Okay, as I said, we use 50,000 color image, and we put, it's the first stage. We put the 50,000 color image, and this image is 3 vector dimension, and we transform it in a linear vector. This linear vector has 3072 input data, and use these inputs to feed the neural network. Okay, and as I said, the autoencoder is a self-supervised learning. We use the same data in the input layer, and use for the output layer. Okay, and for testing GLN, we create 3 models. The first model is GLN, and the other model use the TAN activation function and SYN activation functions. Why? Because GLN use 2 components, and the first component we use the SYN for the global components for GLN, and the local components for GLN we use the TAN components. And for comparate, we use these 3 activation. And we create 5 other models which has different compression ratios for the autoencoder. The original image has 32 by 32 images, and we compress in the first model for 24 and 24 image. Compressor rate 25%. The second model 20 by 20, and the third 60 by 16, 12 by 12, and 8 by 8. Repeat 3 models, 3 activation functions, and 5 different compression rates. Okay, we see the values of the neurons here in each layers in the autoencoder. We start with 3072 input data, finish the same number, and the bottleneck has the first model 178, the second 1200, and the third 768, and the fourth model 432, and the 192 numbers of neurons in the bottleneck. Okay, in the second stage, we get the 10,000 images, the color image, the same. We transform it in linear vector and use to feed the submodel encoder to compress these images for use for the classifier. The process, the compressed image, we evaluate in wide residual network, and the other classifier SVM. Due to stochastic behavior of the neural network, for each configuration of the model described, we get 48 experiments, 48 samples for each models. And we use the KS test, called Markov-Sirmov test, to confirm or refute the statistical significant difference in performance between the models. The results. First, the result by the first stage, autoencoder training. here we see the mean value of the magical for each bottleneck layer. We have 3 activation functions and 5 different compression rates. In highlights, we see the 10 activation functions obtain the best performance for the logs function. And in scene, obtain the best loss functions for the other the more compressed models. But on the other hand, we see the GLN obtain the most speed for convergence, and here we see the same results, but in the box plot for the bottleneck layer, and we see that all samples in the box plot. Here we have the box plot for the alpha weights, and as I said, the alpha weights is the weight shows the importance of each component of the activation function, and if equals to 1, the GLN shows the global components in activation, and if 0, the local components, and as we can see, when I increase the compression of the autoencoder, the alpha value is increased, shows the global components. When the information compression is strong, the behavior is adapted for the characterization of the information through the global function. As the compression decreases, the network starts to increase the importance of the local component, as I said. Okay, the next step, the result of the next step for the classification, we evaluate the accuracy of the wide residual network, use the 10,000 image, and we obtain the average accuracy of 70 ohm only for the base for comparison. And here we see the mean value of the accuracy for each bottleneck. As we can see, the GLN obtained the best result of the not thin bottleneck, the 172 and 28 and 1200 number neurons on the bottleneck, and the different results for the ESBM. The GLN obtained on almost the inverse of the results in GLN. WRN obtained the TAN is performing better for the most compressed, and in the other side, ESBM sign is better results. Here we see the box plot of the accuracy, and we see the values of each different bottleneck values. As we can see, the GLN obtained the best results, and the maximum values of the GLN is almost in all the bottleneck, and the size of the bottleneck. Here we see the classification reports that's confirm the superior performance of the GLN for compression values up to 50%. And as I said, we use the KS test. The KS test is a B-sample test, is a non-parametric test used to compare two samples. And the alternative is, the new hypothesis is that the two population distributions are identical. And the alternative hypothesis is that the two distribution sampled come from the different population. And if we see the results only in the 768 and 432 is not is not passed in the test sample, and this means that is the same distribution here. Okay, for conclusion, the latent representation learned by the autoencoder model with GLN was the most robust for compression greater than 50% in WRN, and the high precision for compression above 50% when used as SVN classifier. The use of the GLN brings superior performance in training speed in all compression variation in relation to isolate activation function with the experiments. The ability of this neuron to adapt to image classification problem are all also proven. Okay, the future work, we are testing the several other GLN compositions and other types of the problems in different data sets. Okay, thank you. Question?
Thanks. Are there any questions?
Hi. Well, I'm not an expert in neural networks, but I'm curious. So the objective is of this GLN is they are faster to run.
Faster and try to increase the performance too. Yes.
And the fact that you are compressing using autoencoder and then classify, what is the advantage of that? Because you could. What is the advantage of using a compression like with the autoencoder and then do the classification against classifying directly? What is the advantage of that?
We use the autoencoder to see how the behavior of the alpha value of the GLN, because we variate the compress ratio, and we would like to see the variation of the alpha and prove that GLN is adapted to use the best activation function for the different situation.
Thank you. Another question. You said that as future work, you will plan to do the experiments on a larger data set. Is that right?
Yes.
The results depend much upon the homogeneity or diversity of the data sets used, which type of images you use, or which type you are planning to use in the future.
Yes, we can use in the different data sets. We see because the GLN prove that is sometimes for this situation sometimes is very good to use the GLN because we adapt and we need to test more in different data sets and other composition because we use only two different activation functions. One the TAN, the other is the SIN, but the TAN is the most used components activation function used today, and we see the experiment different order for the SIN and global components. We have the other new activation function like growing cosine is a very new kind of activation function, and we have how can I say in English? We come back to use the periodic activation functions and prove these activation prove the best performance. And for the other side, we have the other activation with the component local. And yes, we can study more about the behavior.
Thank you very much.
Thank you.
Okay, we move on to the next presentation. This will be by Bastos Filho, and the presentation title is Classification of Patients with Diabetes by Analysis of the Patterns of Proteins Present in Saliva using Machine Learning Algorithms. So, please, Carmelo.
Okay, good morning. It's a pleasure to be here again. Okay, we'll try to do my best to do the presentation as quick as possible since we are running on the cough break time. This work was done by a former student of mine, a master's student called Rodrigo Simões, and a former PhD student that's now a professor in the Catholic University of Pernambuco. And the problem that we are trying to tackle here regards on diabetics. Okay, it's a widely spread disease that has lots of people around the world. Roughly, the numbers from 2021, we have more than 500 million people with diabetics. And the biggest problem is that almost half of them, they don't even know that they have this disease. Okay? And the worst part is that the numbers tend to increase in the next decades. Just for you to have an idea, in Brazil, we have these numbers. We have roughly 15 million people with diabetics, and around 5 million do not know that they have diabetes. And the government spends roughly 43 billion of dollars in expenses in the health system. So it's something that you have to take care. There is a very easy way to know if you have diabetes, and there is an easy way to control the disease. Of course, nobody wants to have this kind of disease, but you can have a tiny equipment in which you can have a drop of blood, and then you can measure the rates and see what's happening. The point is that it's not so comfortable to have to every day you have to make something with yourself and have a blood drop, and it's uncomfortable. And because of this, we have this research question, trying to find a way in which we can find a suitable solution to have a comfortable life for people with diabetics. So the idea here is to use the saliva of people to try to identify if a person has diabetes or not. Okay, so it can help to people to prevent themselves from the peaks of diabetes, and can help to diagnose for people, for those who do not even know that they have this disease. And to do this, we have a good collaboration with a lab in Portugal. It's called Saliva Tech. We have these two good friends over there, Professor Nuno and Eduardo, is a PhD student, and they developed a kind of methodology to assess the fluorescence using equipment that is quite tiny, and it's easy to use. Okay, this equipment is based on electrophoresis, and the idea is just to using a tool. You can take the saliva, and then the equipment can analyze the profile of the saliva, the proteins that you have in the saliva. And what we have observed is that depending on the who is doing the exam, you can find different patterns in this electrophoresis. And the goal was to find if there is some difference between groups of people that they are healthy or they have diabetes. We had a first work that we presented in this conference in Portugal, in which we defined some features in this electrophoresis data, and based on the features that we have selected, we tried to group this using clustering algorithms. So we managed to separate people that use it to have the diabetes and healthy people. So the next step, the goal now, is to try to create a methodology. It's a kind of application paper. We are not using the rocket science here. We are using basics of machine learning to create a system that can be plugged in the machine and can provide alerts to people that may have this kind of diabetes. So we have these steps. It's quite straightforward. We make a data collection, create a database, analyze the raw data. So we performed some pre-processing, then we created some machine learning models and assessed the quality to decide which one we should use. Okay. just to give more information about what we, how we acquired the data. The data was acquired by people from the Catholic University of Portugal, Campus Viseu. Here you can see some of the information regarding the equipment and the concentration of proteins that they are using. And what we have is the weights. We have 359 values of protein molecular weights from the range from 10 kilodaltons until 121 kilodaltons. Okay. For this study, we collected data from 170 patients, and we have 118 healthy people and 52 with diabetics. And what we have observed is that we have a ground noise, so we had to do some pre-processing to avoid negative values, and then doing this pre-processing, after this we normalized the values and added a dependent variable to identify if which one of the patients were healthy or has a diabetes. So what we have is that the original database, we used to have roughly 70% of healthy people and 30% of diabetics. So what we did is to create, to apply a oversampling process to generate synthetic profiles for 94 unhealthy people using this kind of application that I presented yesterday. This is the kind of application that we used to do. Then we separated the data for training and test, and we performed 40 trials for each one of the configurations for each one of the machine learning models. So we used very common procedures to find the hyperparameters for the algorithms. Here you can see the values that we achieved for the database that we're using. We tried the support vector machine, logistic regression, random forest, and multi-layer perceptron. Okay, as you can see, the values for the machine learning models are quite regular. They are not they are very regular ones. Okay, here you can see the results for the preliminary tests, and as you can see, we achieved a median. The median that is higher is for the support vector machine with accuracy around 100%, but where we have a distribution of roughly half of the points between 0.94 and 1. Okay, the results for the accuracy were better for the SVM, and then we were interested in analyzing and assessing the other metrics for classification. And as you can see, for the precision, again, the support vector machine achieved better results, and we were expecting to have this. The recall was roughly the same for SVM and logistic regression, and we achieved better results for F1 score for the SVM model. Okay, here we are just analyzing the confusion matrix for the SVM model. As you can see, we have one false positive, and we analyze that maybe it could be a kind of noise in the measure process. And as a conclusion, we just show it that from preliminary results, we can have good and promising results for support vector machine applied to solve this problem. As I mentioned, it's a kind of application problem that in the field of machine learning is not a big stuff, but if you look at the area, it can improve a lot of process and give good quality of life for people that are using this kind of tool. Okay, and for the future, what we are planning to expand the database to confirm the results and assess the methodology for other diseases. Idea is that if you can find these patterns in the fluorescence, you can try to give some alerts for the doctors to say, okay, you have to check if you have diabetes or if you have any other disease, and then you can improve the quality of life and the lifestyle of the people. Okay, that was a.
Thank you very much. Are there any questions?
Very interesting, Carmelo. My question deals with the practicalities of that. So, obviously, to puncture your finger every day, it's not a good idea. But this is to measure the direct level of sugar in your blood. Your method seems to be an indirect one. And how effective will it be to assess the what it matters, which is the level of sugar? Because by investigating the proteins, you are just going to say if somebody has or not diabetes. Am I wrong?
You're right. The point is that maybe we think that if you have a higher level of sugar in your blood, it will provides another level of fluorescence in the exam. So
no,
you can
that I understood. Okay. Yes.
So maybe you can try to access what's happening. And you're right. Maybe with this equipment now we cannot do it, for example, at home. But the point is that maybe evolving this type of equipment, you can buy it as you buy, for example, the equipment that you can assess the blood pressure or the stuff.
No, I understand. This is work in progress. My question targets what is needed once you have diabetes is to assess the instantaneous level of sugar. Okay, because by the proteins, do you have any feelings that the level of proteins could indirectly translate into the levels of sugar? Because this is what it's important.
I see. I don't know. I have to be honest with you. I don't know. I'm not from this field. I'm the guy that provides artificial intelligence tool for these guys. But actually, we can try to seek for this. Okay. Mm-hmm. But the point is that what we like to see if you can find a correlation and to find some outlets for people that do not even know that they have diseases, and then you can say, oh, take care about this.
Yeah. Okay. Thank you.
Thank you.
Hi. Thanks for your presentation. It was very interesting. I have some questions regarding if you take into account things like if the behavior of this tool is fair according, for example, to difference in sex or age ranges, and also on more like I wouldn't say racial, but from different characteristics of the population, because I'm not an expert on diabetes, but in some diseases you have differentials from the biological point of view that take into account this aspect. So I would like to.
Okay, it's a great question. It's a great question because what we have discussed in some of the meetings that we had in the past is that about the distribution of the population, the features of the population that we are dealing with. And what they said is that this population is very controlled. So it's very well distributed, and when they acquired the data, they had this kind of how can I say, of care. Okay, but one point for the future is when we have more information, when we have information regarding different ages with child and children and elderly and women and men and white and Spanish and Hispanic people, so on and so forth, to try to find if you can have a kind of profile across different populations.
Okay, thank you. Any other question? No? Well, thank you a lot for a very interesting presentation. We will have now the coffee break. we'll have 15 minutes, 10, 15 minutes coffee break because well, we are a bit over time. Okay, thanks.
Hola. Hola. So, hello everyone, welcome back. We are now starting our second remote paper session. And we begin with the presentation by Rodrigo César Lira da Silva, entitled Boolean Binary Gray Wolf Optimizer. So, Rodrigo, you are welcome to start. Thank you very much.
Thank you. Can you hear me? I guess it's okay. Morning, everyone. Can you hear me? Yeah? Okay. It's a pleasure to be here. As she said, my name is Rodrigo Lira. I'm a PhD candidate from the University of Pernambuco, Brazil. And now I'm going to introduce our Boolean binary gray wolf optimizer. This paper was developed with Mariana Macedo from Center for Collective Learning, University of Toulouse, Hugo Valadares, my co-advisor from the Federal University of Technology, Paraná, and my advisor, Carmelo Bastos Filho from the University of Pernambuco. Here is my agenda, and I follow the section from our paper. So let's start. Better binary optimization algorithms are vital for solving real-world problems. Last year, we published an overview in binary optimization in IEEE Access, and we noticed that many of the binary swarm proposals were a direct translation of the continuous version using only transfer function to work in binary space. Even though this proposal can converge to optimal solution, the computational cost is higher than the necessary since it uses continuous operation. Also, the movements in continuous space do not always translate into the binary space. In our research group, we have been investigating Gray Wolf Optimizer, GWO, since 2020. GWO presents a good performance in optimization problems. Considering the promising results of Boolean operation for binary problems, we propose here the Boolean binary Gray Wolf optimizer, BBGWO. Allow me to introduce GWO. In nature, gray wolves live in a pack, and they organize themselves in a strict social hierarchy. Alpha, beta, and delta are at the top, followed by the lowest level, the omegas. Also, the wolves hunt in a group, following a specific set of steps. Inspired by the mentioned behavior, Mijalili et al. Proposed Gray Wolf Optimizer in 2014, GWO. In the proposal, each wolf represents a candidate solution, and the three test agents are considered alpha, beta, and delta. In the movement, the entire swarm is attracted by them. Now I'll show you our binary proposal. We created the Boolean binary Gray Wolf Optimizer, BBGWO. It is a binary version of GWO that uniquely operates in the binary space. Our agents are binary vectors, and the interaction are also performed in the binary domain, using Boolean gate as or, not, and sure. XO, sorry. We added a hyperparameter called modification rate, represent the number of positions changed per iteration in each agent. Our proposal is simple to implement, and it follows the same GWO pseudocode, as we show here. We only change the movement equation. Here you see that we apply our movement equation in the selected D dimension that we choose based on the modification rate. Let's see the movement equation. In BBGWO, we have two kinds of behavior in the movement equation. If the swarm is changing its fitness, we use the first one, where we calculate the new position as the output of an exclusive OR, using as input each leader influence, alpha's influence, beta influence, and delta's influence. The leader's influence is calculated using a 3-input majority gate, which receive as input the leader's bit, the agent bit, and a random bit. These are when the fitness keep change. As a second behavior, when the swarm is stagnated, we only flip the selected bit to create diversity in the agents. Now I'll show you our experimental setup. We used 1max and 0max. They are two opposite problems where we need to find the maximum of 1s and 0s respectively. Also, we simulated the 0-1 knapsack problem where the challenge is filling the items into a bag, a knapsack, in an efficient way. We have 3 scenarios for each problem using 10, 50, and 100 dimensions, with 30 agents in all of them. We performed 30 simulations for each scenario with 1,000 iterations per simulation. We compared our results with 3 binary optimizations, binary PSO, BPSO, BGWO1, and BGWO2. BGWO1 and BGWO2 are binary GW version that use continuous operator. Now let's see the results. Okay, figure 4 shows the fitness values reached by our proposal. Change the modification rate or hyperparameter for 1max, 0max, and 0-1 knapsack problem. When we consider only 10 dimensions for the problem in A, D, and G, we see that the swarm converges similarly. As the 0-1 knapsack is more complex than 1max and 0max, we observe that in some scenarios, the performance decreases as we increase the number of flipped positions. I'm talking about the H and I. When we increase the modification rate, the performance decreases. So based on the results, we propose that for these scenarios, we use the 10% for modification rate. It is more appropriate. Here, we demonstrate that the BBGWO can overcome common binary swarm algorithm limitations. We used the most complex problem to discuss this dynamic behavior. It's 0-1 knapsack with 100 dimensions. In figure 6, we show the majority. In the majority of the time, the swarm is not in the same position. Here we see the unique counts. We also identify multiple points in time that the swarm changed from entire diversity to half of the swarm being in unique position. In figure 7, we can measure the Hamming distance among agents as a way to estimate how near the edges are to each other. On iteration 220, we observe that the swarms increase the distance among each other and converge again. It happens over and over again. Using both figures, we demonstrate that BBGWO can overcome premature convergence, and also it keeps agents in different positions most of the time. Now let's see the fitness. The results from 1max are shown in figure 8. In A, we see 10 dimension. Here we see that all algorithms have similar results, but in C, in 100 dimension, we see that BGW1 is slightly better than BBGWO. Additionally, BGW2 here found the worst result in the problem. Now, in 0max, we found a similar behavior, but BGW2 changed place with BGW1, as shown in the figure 9B and C. So now the BGW2 is better than BGW1. Again, using 100 dimension, we see BBGWO, which good results, but BGW2 is slightly better than our proposal. 1max and 0max are two opposite problems. We observed that for 1max, BGW1 performed better than BGW2. And for the 0max, BGW2 performed better than BGW1. We believe that this may be due to a biased operation to one direction in each algorithm. In contrast, our proposal showed near optimal results in both problems. Now I'll show you the knapsack results. Figure 10 shows the results from the most challenged problem using your simulation, the 0 knapsack. Here we see BBGWO, a proposal, outperforming the other algorithms in 50 and 100 dimensions. I'm saying about the B and C, or BBGWO proposal is outperforming the other BGW1, BGW2, and BPSO2. Now, using a confidence rate of 95%, we apply the Wilcoxon test to compare the efficiency across algorithms. In general, BBGW has a better performance than the other algorithms for 10 and 50 dimensions, as shown in the table 1 and table 2. Here's them. For the case of 100 dimension, we observe in table 3, BBGW also outperformed the other algorithm. However, in the case of 1max and 0max problem, BGW1 and BGW2 were slightly better than our proposal. Now let me summarize the main points. We propose the Boolean binary way of optimizer. A proposal incorporates only binary operator using logical gates. BBGWO has high accuracy and simple implementation. The results showed a balanced convergence that allows the swarm to explore and exploit quickly but carefully. Using 1max and 0max, BBGWO showed promising results, demonstrate that's not biased in one direction. Using 0 and knapsack, BBGWO displayed better performance than the others as we increased the complexity. For future work, we will compare the proposal with other evolutionary and swarm-based algorithms and apply it to other problems like feature selection. Also, we will simplify the parameterization of BBGWO by using an adaptive behavior, swarm behavior. That's all. Thank you for your attention.
Thank you very much, Rodrigo. Is there any questions? Thanks, Libertad.
Hola. Hello. Can you hear me? Okay, I was wondering, thank you for your talk. I was wondering about the dimensions. How important are they and why?
Okay. In this work, we try to use lower dimension. We use 10 dimension, also 5th dimension, and 100 dimension. We try to explore all kind of options, but I don't know if the question is, we don't have nothing related to dimensions. The algorithm will run in different dimensions. Or are you asking about the selected dimensions? Maybe it's another question.
We are asking about
okay.
that.
Sorry. Well, we saw in previous work that the performance of algorithm is impacted by the dimension that is changed, and we are talking about the binary optimization. So we used a hyperparameter to control the quantity or the number of dimensions that we will modify. We also it's possible we change it changing the number of dimension, change the modification rate or hyperparameter. Is that okay?
It's okay? Okay. Thank you very
Thank
much.
you.
Does anyone have any questions? Additional questions? No? Okay, so thank you very much, Rodrigo, for your talk.
Thank you.
And we now introduce Kania Araujo, I think. And the work is the name of the work is assignment of bug reports to software developers using a multi-population evolutionary method. So Kania is when you're ready. We can see you and see your screen. And we hear you, so you can go ahead. Thanks.
So, good morning. My name is Kenya, and I am a student of the master degree in the Federal University of Piauí. And this is my work. This paper is my work for this degree. So the title of my paper is The Assignment of the Bug Reporters to Software Developers Using a Multi-Population Evolutionary Method. So it is the summary of this presentation. So let's start with the introduction. So nowadays, software companies have to deliver increasingly complex products. Due to this complexity is expected an increase of bugs and failures, producing inaccurate results or unexpected behavior during the execution of the software systems. In this context, this paper is focused on performing a bug reporting assignment to developers, but it is balanced with each developer's knowledge and the workload. So based on this, I can say that this work and contribution is the development of an automated process for assigning bug reporters. So now I'm gonna talking about our approach. So our approach works with some inputs, and it has 3 steps. As inputs of the process, we need to have bug reporters from the system that we use to control bug reporters, exceptions and a file with the error, and a Git repository. So with these three parts, we can start working with our process. On the next slides, I'm going to show each step. And in the end, is an output. We have the reports assigned to developers. So the first step is called pre-processing. On this step, we're gonna make the calculation of three metrics. The first metric is called effort, and it is the estimate from similar bugs previously resolved. On this work, we call similar bugs that tools that have the same exception. For example, no point exception. For each bug similar found, the files that were changed on these bugs are identified. So the next metric is called domain knowledge. It's the amount of interactions, notes, or comments that each developer made in a bug report management system associated with the component that presents the error. The next metric is called frequency, and it's obtained through the numbers of comments that each active developer performed on the file with the error. And the last one is called recency. Recency is the difference in days between the current date and the last comment performed by each developer on the file containing the error. Just to clarify, all these metrics are explained in our paper. We explain why we are using each of them. So as the output of these calculations, we go for the next step. We called this metric calculation. On this step, we will calculate the developer's workload. And it is calculated by summing the predicted effort to fix each open reporting assigned to them before. As you may know, in a system that control bug reporters, we have status to the bugs, and we consider just those ones that are still open, because that one that are closed doesn't count anymore and for the workload. So the next step, we're gonna calculate the affinity. And so to extract a single value that represents the developer affinity, we use a fuzzy inference system like this. In the picture here, we can see that we have is an input frequency, recency, domain knowledge that we calculate in the step before. And after the diversification, we have the affinity here, is a single value. So after that, you go through the next step that we call heuristic optimization model. On this step, we choose golden ball heuristic to make the attribution or the assignment to each developer. On the next slides, I'm gonna say why we choose this algorithm. Just to say that golden ball is a new heuristic that uses the football concepts and to solve the combination problems. So I want to say that the objective function for the problem is the maximization of affinity for a balanced distribution of the workload. So this is our function that we're gonna to maximization. Now I'm gonna talk about the experiments. So about the data set. The proposed approach has been applied in a private database of the Integrated Management Systems of the Federal University of Piauí, also called SIG. These systems use a log database to store the stack trace generated when a handle exception is activated. So when a bug occurs, the system registers this on the database. So we can use this stack trace to extract the file, and from the file we can make the calculate the metrics from the Git. Experiment details. So experiments were performed for the reporters batch, assigning from 7 to 19 reporters to 13 developers. These values are because we have this number of the developers activity on the time we had to simulate. And this number of reporters, because it was the number of reporters we have in one day. The mean of values are 7 to 19. So that's why, because we use these values. So now I'm gonna show the experiment details and why we chose the Godeball algorithm is a metaheuristic. So the first test, we made a comparison in Godeball and a brute force algorithm. On here you can see that the brute force has got some results, but when the number of reports increase, it consumes a big time to give their answer. So comparing with Godeball, we can see that the average of the results are so close of that one finding the brute force, and in a time in seconds, still in seconds. And when we're talking about the 10 reporters, the brute force takes 2 days to have the answer. And here I also want to show that the standard deviation is so small, which means that the difference between the big and the smaller values are so close. So comparing Godeball and virtual force, we can see that the Godeball has got close values from the brute force. So on next move, we compare this Godeball with two generic algorithms. Why these algorithms? Because the Godeball are a genetic use concepts of football, but it's based on those algorithms. So we compare the Godeball with the genetic algorithm and the distributed generic algorithm. In a quick close here, we can see a column called the best no value here, and the best value found when we run Godeball genetic algorithm and the distributed generic algorithm. So as you can see, we make in bold the values that are close to the best no solution. So as you can see, Godeball has found the best solution, and all instance we had the calculation. And as you can see, through the standard deviation still is so small. To see the full configuration we used in those algorithms, you can consult our paper. So after confirming that we can use the Godeball, we now use this algorithm on our approach, and we compare these results with the results from the genetic and the distributed genetic algorithm. As you can see in this figure, the Godeball with this color has got the workload so balanced, except by one case, the developed well, but it happened because this case, one bug reporter was measured with a great value. So this developed was associated with this unique reporter, and got the big value. But in the other cases, it was so balanced and so close. What the problems we have here is because the developed one doesn't got any reporter on when using Gundebal. So later are you talking about this? So the conclusions in the research continuity. So this work proposed an approach based on evolutionary method heuristic that used information related to the developer's workload and data about previous fixed bugs to suggest the most suitable developer to fix a new bug. So the threats to validity. To use the use of affect lines in similar bugs fixed to estimate the effort of the new one. So the problem is this could conduct is a disregard the time required for analysis and error identification. Another problem is the coding style of each developer influences in a greater or less number of lines. So for the future works, it intends to adjust the proposed method to be sensitive to new developers. Because as I showed before, when we have new developers, this approach does not associate to new develops new reporters. So in addition to improve the code to estimate the effort to fix a new bug whose exception error type appears for the first time. It is also intended to conduct a qualitative validation of the proposed approach by applying evaluation it in a no-simulate environment. So here I have the references, and that's all. I'm open to questions.
The mic wasn't on. Thank you very much, Kanya. Is there any question here? I have a question. I don't see how do you represent that not all the bugs are equally easy to fix. It seems that all the bugs are equally hard, or maybe I missed something. How do you represent this aspect? Because it influences the model, but also the test and experiments. It's not easy to say, okay, my baseline is this, with all these bugs, and my experiments are fair because I'm comparing with the same kind of difficult bugs in the other case.
I don't understand the question. Would you repeat, please?
Again, okay. I don't see how do you represent, how do you take into account in the model and also in the experimentation that each bug is not equivalent to another bug, because bugs have inherent complexity. So it's not complexity in the terms of not computational complexity, in the terms of difficulty to solve them. So how do you deal with these differences in the difficulty of the bugs? Not the difficulty of the bugs, but how hard it is to fix them. Okay, how hard it is.
Yeah.
Okay.
Yeah, we calculate the value of the number of lines. It was the value we used to make the complex to resolve. We choose this because based on others' works, previous works, and we see them in our work.
Is the number of lines
that
were involved in each one, which you know after you fix it. But before fixing it and before in experimentation time, maybe it's good to take them into account, the distribution and that kind of things. Okay.
That's why our work that we put this is future work, because if we have a new kind of error, we don't know how to count this. So it is a problem that we're gonna work to solve and make using another techniques to solve.
Okay, thank you very much.
Thank you.
Is there any other question? So thank you, Kanya. And
thank you.
Next, we move to our last talk, and we welcome Guilherme Fernandes. And the name of the paper is Tuning of PI Controllers for Electric Drives Using Evolutionary Multi-Objective Optimization Algorithm. We are now seeing your screen, Guilherme, so you can go ahead. Thank you.
Hi, good afternoon to everyone. My name is Guilherme, and I will be presented our work entitled Tuning of PI Controllers for Electric Drives Using Evolutionary Multi-Objective Optimization Algorithm. In this paper, we want to present the use of a multi-objective evolutionary algorithm, NSGA2, applied to the tuning of a set of PI controllers for an electric drive with position control. A DC motor drive is considered with 3 closed control loops, armature current, speed, and position. The outputs of the PI armature current and the PI speed regulators are limited by using saturation at the output of the controllers. Then it is possible to use higher gains for the controllers. Then it is possible, what makes the system to respond faster. However, the wind-up phenomenon can arise, and to avoid it, anti-wind-up circuits are used, and therefore the system is nonlinear. Here we have in figure 1, we have a general multi-objective meteoristic optimization controller tuning. When we have a plant with a control system associated, and the parameters of the controller is adjusted by some multi-objective meteoristic algorithm, and this is done from a set of evaluation functions. And at the end, the algorithm returns a Pareto front, and for be a engineering problem, it's common to be a decision-making stage where we can choose one of the solutions to determine application, and these solutions represent the final controller parameters. In figure 2, we have the block diagram of the position control of a DC motor drive. We have 3 control loops. The inner one represents the armature current control loop, and the one in the middle, the speed, and the outer one, the position. In this work, the armature current and voltage are limited by using a saturation block placed at the output of the PI. However, due to the limitations imposed to the controller's output, the wind-up is inevitable, and anti-wind-up circuits are necessary, what makes the system nonlinear and the task of searching the best tuning more difficult. In figure 3, figure 3 shows one of the basic anti-wind-up circuits as proposed in the literature. Use a a dead zone block to limit the integrator's action. And the application of the NSGA2 to the controller tuning, each individual is a 8-column size vector. The first 6 columns are used to represent the proportional and integral gains of the PI controllers, whereas the 2 remaining ones to represent the dead zone block window limit. And to evaluate its solution, 3 objectives related to the classical parameters within the control theory must be reached. Steady state error, rise time, and overshoot. In table 1, we have the limits of search space. All the proportional and integral gains has the range 0 to 20 real numbers, and the dead zone of the current controller has the range 0 to 220. Some parameters of the system and the algorithm. The maximum step input reference position was set up to 100 radians with 5 Newton meters constant load torque. The simulation window time was set up to 5 seconds. To the NSGA2 algorithm, the population size was made of 80 individuals, crossover probability equal to 90%, and the mutation probability, the inverse of number of variables. And the number of fitness evaluation was limited by 5,000. The DC motor drive was developed in the Simulink environment, whereas the NSGA2 algorithm was run in MATLAB. In figure 4, we have the results. As expected, the algorithm came out with a set of non-dominated solutions where the conflicting nature of the objectives is evident. For example, solutions with a short rise time lead to response with overshoot. On the other hand, response with less overshoot and a small steady state error display long rise time. And in order to show the different possible behavior of the position response, a making decision method, the weighted sum model, was used. As it can be seen, the position response is different, and when different objective is prioritized, for example, the response with the faster rise time displays overshoot, whereas the one with the smallest steady state error presents long rise time. According to the trade-off between all the algorithms, the position response that complies with the objectives having the same degree of importance has shown more appropriate when the fast position control with minimal steady error and overshoot matters. Some considerations about the tuning of controllers. The results shows that in a general way, high values for the proportional gains were achieved, high values for the integral gains too, accepted in the position controller because we don't have a limitation on the output of this controller. The window of the unwind-up circuit of the PI speed controller was set up to values close of the motor current needed to drive the load torque, and the parameter of the unwind-up circuit of the PI current controller presented a large standard deviation. It means that the unwind-up circuit to limit the action of the PI current controller was not necessary since it was not active. And some conclusions from the results obtained by the NSGA2, it is clear that despite the nonlinearities and the number of parameters to be optimized, the algorithm reached convergence after a very small number of runs when compared to the universe of different possibilities to be exploited, providing to be a powerful tool to be used for application in electrical drive systems. And for future works, it is intended to compare the NSGA2 with other multi-objective algorithms, as well as apply them to different types of controllers, different types of motors, for example, such as fuzzy logical controller. And thank you for the attention.
Thank you very much, Guillermo. Do we have questions? I have a small question. As I know, it's frequent, and you said so that all these results are simulation results, which is very frequent in this kind of work. Do you have any plans of trying to test this in real world controllers and see how does this work and etc.?
Yes, we have this plan, but in this moment, the first moment, we wanna try to different types of algorithms, and the tuning of controllers is not change if I try in a real system, but yes, we wanted to do this, and for different types of motors, for example, we use a DC motor, but we can't. We have this intention to go to other types, and yes.
Thank you very much. I have a question. I have to move.
Hi, Demo. Congratulations for the work. At the end of the work, the algorithms, the output of the algorithm is a Pareto set. Each solution of Pareto set is a configuration of your controller. So you have several solutions, but what solution of the Pareto set is taken to implement it in the real machine?
To choose one solution in the Pareto set, this depends very much of the application. And for example, some case you wanted to position response with no overshoot, for example, and we use it a making decision method to choose a solution with the less overshoot. And yes, we can choose a lot of solutions, but this depends very much of the application. And there's no problem to choose one of that's my answer. It depends on the application, and we, after obtained a Pareto front, we just establish degrees of importance of the objectives and apply to a drive, a motor drive.
So thank you very much, Guillermo. And I think we don't have more questions. So this was the last presentation of this track, and we will go back after lunch. I don't remember the time, Martin. 1:30? Okay.
So see you back. Thanks.